All right, everybody, welcome to the video here for lesson number 5. Today we're going to be graphing logarithmic functions. To be able to understand a little bit more about a logarithmic function, we're first going to start by graphing an exponential function. If you remember from a few lessons ago, we learned that a logarithm is really just the inverse of an exponent. So if we graph an exponential function like f of x equals 3 to the x, this should be an easy one, right? Here are our points that we can get right off of our table of values. So we should have 0, 1, 1, 3, 2, 9. There are definitely other values, but those are the ones that we'll kind of use here. So we have 0, 1, 1, 3, and 2, 9. The rest of the points are going to be decimals. They're going to be down here. One of the things we remember about a exponential function is it is asymptotic, meaning it does not touch something. And what it doesn't touch is the x-axis. So it's going to get really close to the x-axis, but not touch it. Now, if I want to graph the inverse of f, I'm going to take all of those points that we know about f and flip them. So I'm going to have 1, 0, I'm going to have 3, 1, and I'm going to have 9, 2. Essentially what I'm doing is I'm changing the inputs and the outputs here. So I'm going to have 1, 0, 3, 1, and 9, 2. Now, unlike the graph of f, the graph of the inverse of f is still going to be asymptotic, but it's going to be asymptotic not to the x-axis, but to the y-axis. Right? Think about it. If you're switching the x and y values, all of those x values that are going to be really small are going to be in here, all right? Because those were the really small y values in here. So here's your graph of the inverse of f. The inverse of f is a logarithm, right? So that graph that we just made there is a logarithmic graph. So let's talk a little bit about this graph. So let's state the domain and range of f. The domain of f, well, that's going to be all real numbers. So negative infinity to positive infinity. The range of f, well, that's going to start at 0, and it's going to go up forever to infinity. Notice I'm using parentheses there because it's not ever actually going to touch 0. The asymptote line of f is going to be the x-axis. And we all know the equation of the x-axis is y equals 0. There's the asymptote line. Well, if I find the domain of the inverse of f, the domain and ranges of f are going to flip-flop. So the domain of the inverse is going to be from 0 to infinity. And the range is going to be all real numbers. It's going to go down forever. It's going to keep going up forever. The domain is the important one for us to understand that even though in our graphing calculator we're not going to see these points when we eventually graph this as a logarithm, they're there. Okay? The inverse also has an asymptote line. It's the y-axis, which we know is the equation x equals 0. So to find the equation of f of x, so if I have the original equation, y equals 3 to the x, the inverse is x equals 3 to the y. Now we learned in a previous lesson we can rewrite that as a logarithm. So I'd say y equals log base 3 of x. Now, here's what I want you to do. I want you to go into your graphing calculator and graph this. If you're a new calculator person, use log base. If you're an old calculator person, you're going to divide log of x divided by log of 3. Now, I understand that some of you might not have your calculator at home, so I also want to just show you quickly how to graph these on Desmos. So if you're using Desmos as your graphing calculator, you go to desmos.com, go on to click on calculator. You're going to see this screen. You've used it before. And if you click the little button here that has like, it looks like a little keyboard, you can type in various things. Since a logarithm is a function, we'll click function. You'll see there's a bunch of functions in there. If you click miscellaneous, there's a button here for log of a. So if I put in a base of 3, and then in the parentheses put in an x, it'll graph my logarithm. So we can see as this graph is going to continue to get bigger, right? If I scroll across, if I look at my table of values on our graphing calculator. Also, if I zoom in here, you'll see it keeps getting closer to the x-axis. It's not really touching it though, right? It gets really close to it, right? So we have this whole logarithm graphed for us. All right, let's go back to the notes. So, graphing a logarithm. So whenever we're graphing a logarithm without having to graph the exponent first, we have to do one of two things. We can either guess and check at potential x values that would generate output values for us, or we can just type it in our calculator. I know most of you are just going to type these in a calculator, and that's totally fine. But I do want to go through the process a little bit of how we can kind of identify some good numbers to plug in for x. So if I'm plugging in some numbers for x, so if I have this function x and f, I can actually generate this table of values without using my calculator. Again, I know you're allowed to, and I want you to, but I also want you to know where these numbers are coming from. So if I plug in 1 for x, so if I have log base 2 of 1, I'm saying 2 to what power makes 1, and that's 0. So if I have an x value of 1, the output value is 0. So I know 1, 0 is on my graph. Then I have to think, well, what are some other good numbers I can put in there? Like, I don't want to put in 3 there, because 2 to what power makes 3? I have no idea. But 2 to 1 makes 2. Essentially, I'm kind of finding the values backwards from what I'm used to with exponents. So then I could think, all right, so what would be another good x value to plug in here? Well, 2 to the second makes 4. So an x value of 4 is going to generate an output value of 2. See if you can come up with the next good point for us to graph. All right, so I'm hoping that you found that the next one was 8, which generated an output value of 3, because 2 to the third power makes 8. So we have 8, 3. And then the next number after that's going to be 16, 4. So you're going to see, just like exponential graphs, the points are going to start to get really far apart. They're going to grow exponentially, kind of. So when I graph this logarithm, I have to remember two things. One, it's a smooth curve. Two, it doesn't stop here. So if you put this into the table of values, you're not going to see any values smaller than 1, because your table of values only goes up by 1. But we have to remember that logarithms have a asymptote line. So it's going to keep going down. So we have to remember that little, I call this the log tail. We have to remember it's there, all right? So we'll call this f. So let's talk about the domain and range of f. Just like the original one we did in the opening exercise, the domain of this function is going to start at 0, and it's going to keep going up to infinity. But notice I'm using a parenthesis here to show that it's not actually touching 0. The range of this function is going to be all real numbers. Every possible y value is going to be included on this graph. The x-intercept on this graph is the point 1, 0. There is no y-intercept on this graph, right? Because remember, we just said it has an asymptote line. Then it says find the coordinate on this graph with the y value of 1. So a y value of 1, we're talking about this point. So the coordinate of the point with a y value of 1 is going to be the coordinate 2, 1. And just like all the functions we've talked about this year, we have to describe their end behavior. So what happens is x gets bigger and x gets smaller. So notice I'm saying as x approaches 0, it's not going to go past 0, so we're saying as it approaches 0. So if we look at my graph, as the graph moves towards 0, what's happening to it? It's getting smaller forever. As the x value gets bigger, it's going to get bigger forever. So the way that we describe that is as x approaches 0, the function approaches negative infinity, it goes down forever. As x gets larger forever, the value of the function also gets larger forever. Then says ascribe the x values such that log base x is less than 0 and log base 2 of x is less than 0 and log base 2 of x is greater than 0. So here we're talking about two sections of our graph. So we want to look at the part of the graph where the logarithm is above the x-axis and below the x-axis. So this part that I'm circling in green, this is where log base 2 of x is less than 0. The part here that I'm going to circle in red, this is the part of the logarithm that's greater than 0. Less than 0, greater than 0 is just talking about above the x-axis and below the x-axis. So when I'm talking about the part that's less than 0, what's happening to the graph? It's going down forever, right? So what's happening to the graph, right, as the x value, the logarithm is less than 0, the x value approaches 0, the function value approaches negative infinity. What happens when the function's above 0? We could say the x values go on forever, and the function values also go up forever. Right, moving right along, we have a couple different logarithms graphed. So I'm asking you to identify log base 2 of x, log base 5 of x, log of x, and ln of x. Remember, this is really base 10. This is really log base e. And if we remember e from the previous chapter, it's about 2.7. We'll use approximate there. So what we're asking here is compare and contrast the family of logarithms. So how do we know which one is which? Right, that's the first kind of thing here, right? So when we graph an exponent, we're able to identify which one is which because the steeper logarithm, the steeper exponential function usually has a larger base. Like if I asked you to graph 2 to the x and 5 to the x, you'd be able to identify which is which. Well, here we can identify our logarithms pretty easily by just looking at where the logarithm is at 1. So here's a point at 1. Here's a one with a y value of 1. Here's one with a y value of 1. And here's another one with a y value of 1. So where these logarithms are going to have a y value of 1, that's essentially telling you the base. Because when you have a logarithm, when the base and what you're evaluating are the same, the value is 1. So for this point, this is going to be the point 2, 1. So what that means is when I plug in 2 for x, I should get 1. So that means this red graph is log base 2 of x. I'm going to skip the orange one for a minute and go to the blue one because that orange one has a weird point. So let's go to the blue one. This one has a point of 5, 1, meaning this is log base 5 of x. The green graph has a point of 10, 1, which means this is log base 10 of x, which is the same thing as just log of x. Remember, base 10 we could just write as log. It's like shorthand. Leaving us with this orangey colored one. So this orangey colored one is somewhere between 2 and 3, which is approximately my e value. So this is going to be the ln of x. So what we can see is, unlike a exponential function, as the base increases, the graph of these actually flattens out. So what we can say here, right, is as b increases, the function flattens. That's one thing we can say. We could also say all have the same domain and range. Right? If you look at all 4 of these graphs, none of them are going to cross the y-axis, so they're all going to have that same domain of greater than 0. And they're all going to have the same range because they all keep going down and they all keep going up. So if we wanted to sketch a graph of y equals b log base b of x, we know it's going to have an x and a y-axis. We really only care about quadrants 1 and 4, though. We know it's going to come up through the x-axis, The point where it crosses the x-axis, that's an interesting one. Something else that you might have noticed about all four of these graphs up here is they all have the same x-intercept. So we'd even say they share an x-intercept of 1, 0. So my sketch is going to include the point 1, 0. It's also going to somewhere include the point b comma 1, because whatever that base is going to generate a y value point of 1. I just don't know what b is, so I can't really estimate it correctly. But this is a good graph of what we're trying to show here. Okay? Different things happen with logarithms. So here's a really good question. This is similar to one that was on a Regents exam a few years ago. So it says graph this logarithm, base 2 of x plus 3 minus 5. And it says use an appropriate scale to include both intercepts. Now you might be saying, well, you just said that it doesn't have y-intercepts, but because this logarithm has some type of shift, right, this is going to be a left 3 and a down 5 shift. The rule of having a asymptote line is still there. It's just not going to be the y-axis this time. It's going to be somewhere else, and we'll identify that using our graphing calculator. But the first thing we want to do in my graphing calculator is figure out what are these x and y intercepts so I can make sure that my scale is appropriate. So let's graph this one. So I'm going to go to Desmos because I'm going to have a calculator on here. So let's go to log base 2. So I got to change my base there. Whoops. Now let's start fresh. Function, miscellaneous, logarithm, base 2. And then we'll make this x plus 3 and then minus 5. So on your graphing calculator, you'll be able to go right to your table of values. But on mine, I can see that I have a y-intercept somewhere between -3 and 4. And if I scroll over, I see I don't have a y-intercept until somewhere close to 30. Right, it's at 29 actually. So when I make my scale, I want to make my scale go up to 30 here, meaning each of these horizontal boxes represents 3. The y scale, I could just keep 10, like normal. So now if I start graphing this logarithm, I can look for some key points on my graphing calculator. If I just go in a table of values, I'll see a whole bunch of them, right? Let me just scroll back here a little bit so I can see the main area of my graph, right? So it looks like I have a point of 1, -3. So I can graph 1, -3. Right, 1's going to be about a third of the way to 3. We have to remember x-axis is different, right? It looks like I have a point of 5, -2. So 5 is going to be almost a 6 and be at -2. If I keep going, I'll see I have another point at 13, -1. 13, so I have 3, 6, 9, 12. So 13 will be a little bit after that at -1. And I remember at 29, I had a y-intercept, so I'm going to have something that looks like that. Then we have to figure out, well, I kind of know what this graph looks like. So I know it's a logarithm, so I know it's going to look something like this, but I don't know what it's approaching, right? So if I look in my table of values in your graphing calculator, you're going to see that the x values are going to keep getting smaller, and eventually at -3, it's going to say error. The reason why is there's an asymptote line here. So if I look at my Desmos graph, see how it's approaching -3 but never crossing it? So we'll be able to say, all right, at -3, which is just one box here, right? This function is going to come down and just never touch -3. The reason why -3 is your asymptote line is whatever is in here, you can say the asymptote line is equal to that. Set it equal to 0, subtract 3, and I know x equals -3 is my asymptote line. Then on the bottom here, it has some stuff here. So it says describe the end behavior as x approaches -3 and as x approaches positive infinity. So as x approaches -3, the function, which we call just y approaches negative infinity. As the graph goes closer to -3, it goes down. As the x values increase, the y values increase forever. Then it says describe the transformation that maps this logarithm onto the one that's given, right? So this maps this onto the above graph. So that's using all the regular transformation rules that we've done throughout the entire school year, right? We did these with polynomial graphs. We then did them with parabolas. We did them with sine and cosine graphs. Now we're doing them with logarithms. Same thing. And we already identified them. It's left 3, down 5. So we can say, right, is we are going to translate. Let's use good math vocabulary. So it's going to translate left 3, down 5. For number 5, we're really just using our calculator here. This cannot be done using a algebraic method. Well, I don't want to say can't be done, but we don't want to do it that way. We want to do this with our graphing calculator. So in your graphing calculator, let's graph this as y1, and let's graph this as y2. We know how to graph logarithms in our calculator, so we can do that. So go ahead, take a minute, punch all that stuff in. So as you're doing this, if you're doing it on Desmos, there is an absolute value button, not under function, it's here. And you can plug it all in. All right, so you have x squared. Whoops. So -9. Sorry, I'm trying to figure this out with you. Okay. So if we look on Desmos, the nice thing about Desmos is it tells you right away what the points are if you just click on them. There's a point. There's a point. Okay. On your graphing calculator, remember you're going to use second trace and go down to intersect. And we should see that there are definitely 2 intersection buttons, points. Now it does say nearest hundredth, so we could graph this and say we have 2.29. That's one x value. So we have this like weird graph that comes down in 2 different ways like that. But we're looking at these 2 points. Those are the intersection points. So we could say x equals the 2 points of 2.29 and 3.63. Basically the same exact thing we did in the last chapter when we were solving the weird equations that dealt with exponents, but now we can do it with logarithms. It's the same method. And that's it. All right, so hopefully this video helped and you could go through and try and figure out some of your homework questions and make sure that you're, again, I know I said this in the last couple of videos, but try the homework before you watch the video. Please make sure that you actually know what's going on, and hopefully I see you soon.